Okay, student, let's start the class. Okay, all of you getting my voice? Okay, let's start the class. Okay, last time we have discussed the MapReduce word count, which we discussed how the particular uh, map and reduce function is working basically. Okay, and so let's start with the next slide. Uh, that is MapReduce overview. Okay, so now we'll discuss MapReduce overview. So this is the uh, overview of the MapReduce algorithm basically. So there is a job tracker. Okay, from here you can see that here we have job tracker, and there is a name node. There is a task tracker, and there is the data node. Okay, so you can see here this is a SDFS layer, right? Okay, so if you remember name node, uh, data node and the task tracker that we have studied till now basically. Okay, but here there is also one additional things you need to understand is a map reduce layer. Okay, so right, you can see there map reduce layer and name node layer as well, and we have map reduce layer as a data node layer as well. Okay, so what is this the job tracker node basically. Okay, so job tracker knows everything about submitted job. Okay, so it is knowing whoever is busy in the particular hierarchy, uh, where the data node is busy. Data node one is busy. Data node one is busy. Data node two is busy. Name node is busy. Okay, is there any blockage or in tracker is being tracked here basically. Okay, okay. So then uh, divided into okay. Some participants are waiting there. So job tracker will divide the number of tasks. What is the task of the job tracker? As the name implies, that divide the number of tasks into number of parts, and it will decide on which the particular uh, basically uh, particular job will be taken by the job tracker, and a particular job to be executed. Taken means what job will be executed basically. Okay, so continuously communicating in task tracker and and job tracker will also communicate with the task tracker. So if previous job is completed, then it particular data node will be seen, and during the period of ideal time, job tracker will keep a particular job in the queue, uh, and for the task tracker to and complete as well. Okay, so once a node task is assigned to task tracker, okay, so it divide the job into task and decide uh, where to run each task basically. Okay, so uh, to continuously communicating with the task tracker, and the task tracker execute the task means per multiple per node. Okay, so and it also monitor the execution of each task. Okay, clear. So failure of the one data node, then another data node cop up with this, and this continuously sending feedback to the job tracker. This is the overview of the MapReduce algorithm. Okay, so next slide we have data flow of the MapReduce. Here we have two main phases of the jobs are one is that we have discussed already map phase and reduce phase. Okay. So first phase in the left side of the diagram from here you can see that is also we have discussed in detail in the word count of the map reduce. Okay, that's just similar to here that particular phase. So first phase that is map phase. We are going to split our data into in a tokenized way. Okay. So then we are going to mapping of this so that will map to to it a map that is going to convert into key value form, in which form that we have discussed earlier, that convert the mapper convert the input files in the key value form. Okay, and after that they have performed the sorting is performed. Okay, and then comes to the merging. Okay, and finally that will come and merging all the individual output into one single node. Okay, and after that we are going to reduce this data. Okay, and what the reducer is performed, we have discussed earlier. It performs some aggregation of the data. Okay, and then perform, and also here we can see that also perform and store the data in the SDFS and perform the replication to remove the fault tolerance. Okay, so in the right side of the diagram, in detail, it can see here in very first as an input we have a block of input file in SDFS. Then mapper is performed, map task one for each block is performed, and then shuffling and sorting phase is completed by the mapper basically, and then reducer performed its tasks in the reduce task, and that perform the aggregation of the data, and after that from here we can see that the output is written to SDFS by using the data replications basically. Okay, so this one is the data flow of the MapReduce, and this diagram show the key value pair generation that we have discussed earlier by using one of the real life example in the previous class. So I just skip this slide from here. Okay, because it's all about all are very much similar that we have discussed earlier. So now. I'm just using the yarn, okay, WARN, yarn, which is some advanced level of MapReduce. Okay, that is one of the advanced level of the MapReduce, and you can just say from here uh, that just look like this. I'm going to explain. My step to execute a yarn is very first. Initially, as an input, we have a MapReduce program at a client node, and it is just run the job basically. At step number two, we get a new application, and this new application allocated to the resource manager, and the resource manager then basically then you're supposed to start the job of converting of my data from a node manager to application master basically. Okay, so at step number 5 a start the container means you just about start the job of converting my data from your data from node manager to application manager, and then launch also is performed, and finally at the at step number 6 we have start the job that also has the same meaning. Okay, after that finally we have allocate the resource. Okay, allocate the resource basically from here we can see that start a container that run. So this is how MapReduce is perform its algorithms, and map and reduce operation is performed. At the step number 9A and 9B, that is showing the one of the data replication. This one is the perform data replication to remove the fault tolerance to operation basically. Okay, so this one is the one of the advanced form of MapReduce. This is called yarn MapReduce, this data flow basically. Okay, clear. In the next slide, we have a concept of the mapper. Okay, the concept of the mapper is just similar that we have discussed. Input path in the SDFS we have input format, then we'll perform input split. All the data are split into universal size of the unique size of the files basically. Okay, and then it will convert into key value mapping basically there. Then record reader, then it will perform partitioner. Okay, now let us have in that particular slide we have a quick mathematics of how many mappers do you need, because that question may be arise in your examination as well as in your some competition also. That let's have a quick mathematics. How many mappers do you need with respect to number of hard disk or memory capacity I have, and the terabyte of the data that can I stored. Okay, So the number of map is usually driven by the total size of the inputs. Okay, clear? And the total number of blocks of the input file, the right level of the parallelism for maps seems to be around 10 to 100 maps per node. Okay, clear? Although it has been set up to, that is one of the bottleneck. Okay, although it has been set up to 300 maps for very CPU light map tasks. Okay, clear? So task setup take a while, so it is best if the maps take at least a minute to execute. Okay, so thus if you expect 10 TB of the input data and have a block size of 128 MB, suppose you have, okay, and you will end up with the 82,000 maps basically. How it will come? Let's see. So this formula will be used. Mapper is equals to how many mappers is required? That is equals to the total data size divided by input split size. Okay, so in our examples, so 128 MB is the block size, 128 MB is the input split size, okay, and 100 MB is the file size. Okay, suppose so file will take only one block in SDFS for storage, and thus one input is split and one map task we have. Okay, similarly in the second example, so data size is 1 TB and input split size is 100 MB. Suppose. Okay, then what is the mapper? Okay, mapper is equals to total data size. Total data size is equals to 1 TB means 1000 into 1000. Okay, and input split size that it is given here 100 MB. So divided by 100, then it will come 10,000. Okay, so from this formula we can easily compute the mapper. How many maps we require to store you need with respect to number of hard disk or and the memory or capacity for a big data solve problem. Okay. So next we have concept of reducer, that is almost similar, as we know that reducer take the input from the take all the output of the mapper will become an input for the reducer. Okay, so reduce task 1, reduce task 2, reduce task m after key mapping, key value mapping by the mapping mapper. Okay, and it will perform data aggregation, and then output part will be stored in the SDFS readable form, data file system readable form basically, and output path in the SDFS in that particular. Okay, so this is and this one is the speculative execution. Okay, that also in detail I'm explaining how the job scheduler. Initially we have a very first job scheduler we have previously we have discussed submit a task on the node A to process. Suppose submit a task to node A to process. The step number one, node A is the original map task. Okay, so after that, at the step number two, scheduler find out node A is running slow. Suppose that we are assuming, suppose node A start running slow. Okay, so scheduler find out node A is running slow. Then from the task progress, which node has sent. Okay, so scheduler what perform? It schedule submit a speculative. Speculative means a duplicate task on a node, another node, that is called node B. Okay, node B is work as a duplicate map task. Okay, and both of the node A and node B are working on the same task. Okay, and if anyone is working slow, then output will not be delayed by the that particular MapReduce operation. Basically, then the output at the fourth step number 4 we have, if node B completed task first, okay, then it send the final output. Okay, and if node A completed task first, then it send the final output. Okay, so final output is taken, say, from the node B. Suppose if A is working slow, then the final output is definitely will taken from the node B. So all the remaining speculative duplicate tasks, speculative means duplicate tasks, will then be abandoned. Okay, clear? So this one is the speculative execution of the MapReduce operation. Okay, clear. So next we have Hadoop fault tolerance. That is very important. That we have. Okay, Hadoop fault means intermediate data between mapper and reducers are materialized to simple and straightforward fault tolerance. So what if a task fail? Means what will happen if a task fail? map or reduce what will perform. Okay, so it will perform task tracker, detect the failure. Okay, clear. Okay, task tracker detect the very first detect the failure. So I if I have here I suppose I am uh, going to showcase you how well the map reduce function get used for the day-to-day life basically. All right. So we can see here that by all the values of the task take as a failure automatically into message of the job tracker, and job tracker reschedule the task. Okay, and it send the message to the job tracker, and job tracker then finally reschedule the task. Okay, if any failure detected by the task tracker. After that, we have what if a data node fails. Okay, so both name node and job tracker detect the failure. Clear? Name node and job tracker we have discussed earlier. All the tasks on the failed node are rescheduled. Okay, and name node replicate the user's data to another node. Okay, clear. This one is the one of the process of Hadoop, how Hadoop handles the fault tolerance. Okay, and finally, what if a name node and job tracker fails? If this condition occur, okay, then the entire cluster is down. Okay, that is very rare case basically, but because all the tasks are done by in a duplicate manner by performing more than one nodes. Okay, so these all are the possible solution provided by the Hadoop for the fault to perform the fault tolerance. Okay, so this is all about the map reduce. Previously, we have discussed in the last lecture. We have discussed in detail about the map reduce introduction. Then today we'll discuss some more in detail about the MapReduce, mapper and reducer working. Okay, so next in this lecture, I'll just want to cover some more Hadoop ecosystem components like Hive that I have already discussed at introductory level. What is the role of the Hive basically? Okay, so Hive basically provide. We know that it is just working like in a structured query language (SQL) interface. Okay, so Hive provide structured query language interface in terms of Hive QL or the Hive query language. That is also called Hive query language. Okay, so this interface translate the given query in the MapReduce code. Okay, means the query convert these translate the query into the MapReduce code basically. And Hive QL enables user to perform tasks using MapReduce concept without explicitly writing the code in the terms of map and reduce function. Okay, and the data stored in the SDFS can be accessed through HiveQL, which contain the feature of SQL, but run on the MapReduce framework. Means all the all the working are just similar to the SQL query language, but run on the MapReduce framework. It convert or translate all the things in the that is the task of the Hive. Okay, Hadoop Hive basically. Okay, so it is mostly used in data warehouse housing kind of application. We know because queries and estimation are performed with the data warehousing basically, where you need to perform batch processing on a huge amount of the data. Example of this kind of data include web logs, call data records, or bank details, records, weather data, okay, etc. So these are the following way for accessing the Hive. Okay, the Hive command line interface. Okay, one of the method, or another method is Hive web interface. Uh, one more we have Hive server, and very common we have JDBC and ODBC also, through which we can access the Hive basically. Okay, so this architecture, this one is showing the Hive architecture. Here we can see that initially at the application layer we have Hive, and all the interface are there: command line interface, Hive web interface, Hive web interface we have. Then we have a query and compiler executor. They are there. Okay. After that, job tracker and task tracker that we have discussed. Okay, and these all are inputs are converted in finally in the form of SDFS, Hadoop SDFS format. Okay, so this one is the Hive architecture and hierarchy also showing in that particular architecture. Okay, and data types and built-in function in the Hives are very much similar to the SQL. Okay, only the little bit difference with the SQL data types basically. So primitive data types supported by the Hive is teeny int that contain 1 byte integer, small int that have a size 2 byte integer that has size 2 byte integer, int 4 byte integer, big int 8 byte integer. Okay, also some miscellaneous primitive data types are also there, like or to handle the conditional logical operation, so boolean true and false. Okay, binary only available starting of the, that is not right now not available because only starting of the hive basically. Okay, and plotting numbers we have plot single precision, double precision. Okay, so string type also supported by the hive, string, where, care, that is all I think all almost similar with the SQL. And some these are the primitive data types. The complex data types are created just similar in every programming language. The complex data types are created using the primitive data types. The complex data types which are available in hives are struct. Okay, that is dot operator is used to access the element within the type. Structure means okay. Maps, element name notation is used to access the element in the map. Okay, array also support, hive support also the array. Element in an array is used to store the same type of the consequently data types. Okay, so these elements can be accessed where n is represented by the index number, okay, of index number of the array. These are the different data types supported by the hive. Okay, from here you can see that DDL language or data definition language supported by the hive, just similar. DDL commands we have discussed are also discussed in SQL also: create, alter, drop, show, truncate, delete. Okay, all these are the same commands, only the little bit difference with the SQL here. Okay, DDL command, suppose like to create a database means create database MLVTEC Bhilwara. Okay, so here we can write down here. So this database will be create, and then if create database if not exist. Okay, if this one is one more flavor of the create database. If it is not exist, then this statement can also be used. This command can also be used. And if you want to store the data on a particular location, then create database MLVTEC Bhilwara, and that location also is specified there. Okay, means a particular location. If you want store, create a database, then this command will be. Database properties means create database MLBTEC Bhilwara, and with the comment means this comment is added for Hadoop tutorial with like honor is Nitesh Chauhan or any you can put there. And describe also, that is also one of the command, describe database MLBTEC Bhilwara. Okay, so these DDL command, through this DDL command, you just have to make the practice in with your laptops or with available devices. Okay, if you have, okay, because it's very important and very similar, just very simple. Also, you can simply make this DDL commands. For example, show database and show tables. Okay, these are the DDL commands. Show altering means to make some changes, renaming the table, modify column, delete some columns, change table property. Okay, alter table for adding partition, altering storage property, altering database properties. Okay, for example, means if we alter table, okay, means alter table student rename to student basically. STUD rename to the student. Okay, so this one is the one of the example of renaming of the table. Modify of the column is alter table student, change column as name, student name, string. Okay. So I think you just have to go through this and do some practice. Okay. So altering database property, alter table student, add columns. Suppose if you want to add column in the final one, you can see city string. Okay. So you can add the column. You can drop by using the drop command. Drop the table by using the drop command. Drop table if exists student. Drop database if exists MLBTEC Bhilwara. Means just create, drop, alter. Okay, all the operation. I think the practical aspect from here you can see that you can just have to load the data that we have created and select. Suppose that database we have created employee. Okay, and select all the values from the employee. I think it's almost similar with the SQL, and that is a little bit difference in the commands, the syntax. Okay, uh, in the hive. Okay, so select a statement we have load data local. You just have to do this thing into table employee and select name salary from the employee. Select e dot name, e dot salary from employee uh, that have a instance e. Okay, select name technology from employee. Select symbol price star from employee. Okay, these all are I think very much similar with the data you have discussed in database also. Next, we have Hadoop Pig. Okay, Hadoop Pig, we have discussed also that one of the language that express the data flow in the pig Latin form basically. So pig raise the level of abstraction for processing large database. Pig is made up of two pieces. The language used to express data flow called pig Latin. Okay, this one is called, and the execution environment to run pig Latin program. Okay, so pig Latin program is made up of a series of operation or transformation that are applied to input data to produce the output. Okay, so Pig is a scripting language basically for exploring large database. Okay, so Pig was designed to be extensible. Okay, so these are the data types supported by the Pig. Primitive data types and complex data type it have. Okay, so int, log, plot, double. Okay, big decimal, big decimal. Okay, Boolean. Complex data type support map, tuple, outer, inner. Okay, so these are the some of the data types supported by the Pig basically, and these queries can be executed by lot, filter, dump. Okay, we'll discuss in detail all the things basically, but you have to just have to go through some of the books and some of the notes online available. I also share some notes about the pagan hive basically. Okay, so you just have to go through these all the queries because they all are very much similar to SQL and scripting language that you have done earlier in any of the scripting language you have done. Okay, so these are all about the MapReduce, HBase, Pig, and Hive basically. Okay, so we have discussed Hadoop ecosystem, MapReduce in detail, uh, Pig also, Hive also, okay, and the various MapReduce functioning and their in detail architecture also. So you just have to go through all these videos that will be available on college YouTube channel. Okay, so thanks for this lecture.